All right, moving on to the next section, slices. I'll open it up, open my editor. I already erased the print line. The slice type. Another data type that does not have ownership is the slice. Slices let you reference a continuous sequence of elements in a collection rather than a whole collection. Here's a small programming problem. Write a function that takes a string and returns the first word it finds in that string. If the function does not find a space in the string, the whole string must be one word. So the entire string should be returned. Let's think about the signature of this function. Yeah, I've done something like this before. Let's see what it looks like. They have first word, good naming convention, and we're going to take in S, which is going to be a pointer to a string. I guess it's a pointer to a reference to a string. It is a reference to a string because, well, we don't need to mutate the string, so it doesn't really matter. And then we're returning something. They have a question mark, but I can see down here it's usize, and it's probably usize because you need to know the first index where the space is, or the last index of the first word, seemingly. So let's confirm that. This function, first word, has a reference string as a parameter. We don't want ownership, so this is fine. But what should we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word. Let's try that. So yeah, I was right. We're returning the index of the end of the first word. And we write usize because index is of type usize. Let bytes equal s dot as bytes. Okay, as bytes seemingly looks like I'm guessing it's a slice because we've been talking about slices, but a slice of U8. I guess it's UTF-8. For we have a tuple I item, so that's a reference in bytes iter, so we know it's an iterable, dot enumerate like we used this in one of the homework assignments. That's going to give us the index. That's probably this I right there. If item is equal to, we do the binary of a blank space, or not binary, bytes. This B should represent bytes. Bytes of a blank space. Then we return I, which should be the index. And if not, if we get to the very end, then we want the length of the entire string. And did I write something incorrectly? Let's see. For, I forgot a comma. And now we have our types. Yes, usize, which is the index, and item. So let's do a walkthrough of this first before we try to run it or continue. You have a function called first word. It takes in a reference to a string and returns a usize. We're returning a usize because we want to return the index of the last letter of the first word, because we're doing searching for the first word. We're taking in this reference to the string, creating it as seemingly as a slice of bytes, and then we're iterating over that slice of bytes. We have the iterator, and we have enumerate to give us the index of the item that we're currently looking at. Here's the item, which is also a reference. We check to see if this item, reference to the point of the string that we're looking at, is equal to an empty string. If it is, then we return the index of where we're at. If not, we can move on to the next item. And we do that continuously. If we happen to reach the end of the string and we have not hit this line of return, then we come here and we return the length of the entire string. And I'm scrolling down, but I'm not seeing them doing an example of that. So let's do the example of that here. Let's just print out an example. Print call this first word, and we're gonna pass in a string, and that's gonna give us an answer. Put that here, and we can put our string here. Let's call s, let s equal string from, we do hello, let's do hello world, because that's hello space world. See what that gives us. And we have s as our first parameter, because that's going to go here where we're passing in, and then we want to see the answer. So first word, pass in s. Oh, I pass in a pointer to s, and that should be fine. Let's see. Ooh, not sudo update. Cargo run. We have first world hello 5, which makes sense. 0, 1, 2, 3, 4. So that's the 5th space right there. The first 5 letters. 1, 2, 3, 4, 5. If we were to make this one word, maybe 10. How many? Yeah, 10, because world is 5 letters too. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so it seemingly works. That's what it's doing. Let's move on. Because we need to go through the string element by element and check whether the value is a space, we'll convert our string to an array of bytes using the asBytes method listed here. Next, we'll create an iterator over the array of bytes using the iter method right here. We'll discuss iterators in more detail in chapter 13. For now, know that iterator is a method that returns each element in the collection, and that enumerate wraps the result of iterator and returns each element as part of a tuple instead. The first element of the tuple returned from enumerate is the index, and the second element is a reference to the element. This is a bit more convenient than calculating the index ourselves. Very true, it is more convenient. They did explain it. I mean, enumerate just means we have a tuple now, and we have the first element, which is the index of how far we are in the array of bytes. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple, just like everywhere else in Rust. So in the for loop, we specify a pattern that has I for the index in the tuple and a reference to item for the single byte in the tuple. Because we get a reference to the element from the .iter enumerate call, we use a ampersand in the pattern. So this is referring to this. We use enumerate, which gives us a tuple. Hence now we have this tuple. We're deconstructing it, as in this is going to return a tuple of 2 elements, and now we are assigning the first element to I and the second element to this pointer to item. Moving on. Inside the for loop, we search for a byte that represents the space by using a byte literal. So this is called a byte literal. I messed that up earlier. If we find a space, we'll return the position. Otherwise, we'll return the length of the string by using string.length, which is down here. Makes complete sense. All right. We now have a way to find out the index of the end of the first word in the string, but there's a problem. We're returning a usize on its own, but it's only a meaningful number in the context of the pointers of the string. In other words, because it's separate value from the string, there's no guarantee that it will still be valid in the future. Consider the program in listing 4-8. I see what they mean. So what they're saying here is that in this program is nice, it works, but it's flawed. The reason why it's flawed is because we're returning the index of the first word, where the first word ends. But that index is meaningless without the reference, well, without S itself. Because in order to know where the first word ends, you have to go back and plug that number into S. The reason that is an issue is because by the time we do this calculation, S could have changed. S could have been mutable. And if S was mutable and it has changed, then our value is now meaningless and more properly just wrong, incorrect. So now they want us to look at this example. This example has a string hello world, first word, and then we do s.clear. So right here, well, I could do it under there. We say let word equal first word, pass in s again. Now we do s.clear. Oh, we have to make sure s is mutable. So now that we have cleared the string now equals to nothing. It's just an empty string. So this value of 5 that we return back from a hello world that has a space in it is meaningless. The program compiles without any errors and would also do so if we use word after calling s.clear, because word isn't connected to the state of s at all. Word still contains the value 5. We could use that value 5 with the variable s to try to extract the first word out, but this would be a bug because the contents of s have changed since we saved 5 in the word. Having to worry about the index in a word getting out of sync with the data s is tedious and error prone. Managing these indices is even more brittle if we write a second word function. Its signature would have to look something like this. The reason why the signature looks like this is because you need the index of where the second word starts and the index of where the second word ends. So now we're tracking the starting and ending index, and we have even more values that were calculated from data in a particular state, but aren't tied to that state at all. We now have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution to this problem. Alright, so Rust has a solution. It looks like we could take a range of the array. So let's just see what that looks like real quick. Print, yeah, I'm not gonna write their program yet. I'm just gonna test it out here. So let word equal let's call it word index. Index equal first word, pass any pointer to s, and then in the next line let's print out print new line, because it said we can just use the pointer 0 to word index. See what that gives us. Unexpected token. Print And now we have the word. Okay, so we can do this. We can use this syntax right here, which is displayed right here, and use range of the array. Okay? String slices. A string slice is a reference to a string slice is a reference to part of a string, and it looks like this. So this is a string slice, is what they're calling it. It looks like this. We have the start index and the end index. Start, and you range over to 5. This is similar to taking a reference to the whole string, but with an extra bit. Rather than a reference to the entire string, it's a reference to a portion of the string, the start and end. Syntax is a range that begins at the start and continues up to but not including the end. If we want to include the end, we use ... equals instead. So if we want to include the end, we want this number to go down by 1, or we want to have a space. So let's do -1. Actually, no, I can just do the -1 here. And that's more explicit. And we should have the same value. Hello. And technically speaking, if we put the -1 here, that would be equal to word index. Or I can just print out word index. And this again. 4. Alright. So here they have an example with hello world, 0 to 4, including 4, 6 to 10, including 10. The equal means that we're including the last number. If that helps you remember the difference between ... and ... equals, good for you. We can create slices using a range within brackets by specifying the starting index and the ending index, where starting index is the first position in the slice and ending index is one more than the last position in the slice. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending index, minus starting index. So in the case of let world be a pointer to 6 to 11, world would be a slice that contains a pointer to the 7th byte of S with a length of 5. So here's world. It's a pointer to the 7th item, so 0, going to the 7th item, and has a length of 5. And then world, oh, this is S, all of S. Starts at 0, pointers to the 8, and has a length of 11, goes all the way to the end. Similarly, hello should be 0 to 4. With Rust ... range syntax, if you want to start at the first index 0, you can drop the value before the two periods. In other words, these are equal. So these are equivalent. If you want to start from the 0 index, you don't even have to put the 0. You can just omit it, ... By the same token, if your slice includes the last byte of the string, you can drop the trailing number. That means these are equal. So in this example, this is the trailing one, length. You can just drop it. And then similarly, if you just want to go from the beginning to end, instead of writing 0 in length, you just do ... Makes sense. We have a note. Note. String slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. For the purpose of introducing string slices, we are assuming Ascii only in this section. A more thorough discussion of UTF-8 handling is in the storing UTF-8 encoding text with strings section of chapter 8. Okay, just a brief overview of UTF-8. versus Ascii. It's like a storage thing. So let's say ASCII character. This we have an F here. Let's say this takes 1 box to store it. For maybe a Chinese character or a character emoji, it has so much content in it that you can't represent emoji or Chinese character in that 1 box. You may need 5 boxes or 6 boxes or 8 boxes. And because of that, well, that marks the difference between UTF-8 and like ASCII. It just takes, you have more information to be stored and represent. And what they're saying here is that when you iterate over a range, a string slice, you're iterating over the UTF-8 characters. So let's say you had Chinese characters, you had 5 of them, and these 5 characters all have really dense representation, maybe like 10 bytes, 8 bytes. The first index is going to be the entirety of that character. The second index is going to be the entirety of that character. So if you had 5 characters, the length of your array is going to be 5. And when you iterate, you're just going to go from 1 byte to the next, or 1 character to the next, instead of going 1 byte at a time. Because if you went 1 byte at a time, you had 5 characters, and they each had 8 bytes within them, then that's 40 bytes to iterate over. They're saying you can't do that. They're saying that that will cause an error. But I digress. That's not even this chapter. That's chapter 8. Let's continue. With all this information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written. Okay. Yeah, so we're rewriting this now. Usize. You were nice, you were good to us, but we need something a little bit better. So we're returning a string slice. And I guess here we return pointer S. I can see it over there. 0 to I. We can just drop the 0, I. And then here, pointer to S, and just do dot dot. This is no longer an index. Call that a word. You can't minus 1 because they're different types. And that is no longer a thing. And now we can just print out a word. And that should be it. See, look, first word, hello, word. Yeah, that went well. Alright, so skip over that explanation, go to here. Returning a slice would also work for second word function. And this would be the syntax, or this would be the signature of the function. Function, second word, pass in a string, reference to a string, and return a string slice. We now have a straightforward API that's much harder to mess up because the compiler will ensure the references into the string remain valid. Remember the bug in the program in listing 4-8 when we got the index to the end of the first word but then cleared the string so our index was invalid? That code was logically incorrect but didn't show any immediate errors. The problem would show up later if we keep trying to use the first word index with an empty string. Slices make this bug impossible and let us know we have a problem with our code much sooner. Using the slice version of first word will throw a compile error. So I see what they're doing. We have first word. The program stays more or less the same. String, mutable, word. And then if we try to clear S, this is the underlying reference that is still used here. Run the code. Oh, yeah, we have to print it out. I'm pretty sure that if we do something, if we don't print it out, the compiler just skips it. And you skip it for optimization reasons. If we're not using it, why compile it? Meh. So here we go. If we try to print word, now we should get the error that they're telling us we're going to get. And just make sure this is the same. Cannot borrow S as mutable because it is also borrowed as immutable. So that's what they have here. Immutable borrow occurs here. This is where the immutable borrow occurs. And then we try to change it. Mutable borrow occurs here. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference. Because clear needs to truncate the string, it tries to take a mutable reference, which fails. Not only has Rust made our API easier to use, but it has also eliminated an entire class of errors at compile time. That's very impressive. That's very impressive. String literals are slices. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. We have the let s equal hello world, string literal. The type of s here is a, what did they call this? This is a slice, string slice. It's a slice pointing to that specific point of a binary. This is also why string literals are immutable, because this type, pointer stir, or ampersand stir, is an immutable reference. String slices as parameters. Knowing that you can take slices of literals and string values leads us to one more improvement on first word, and that's its signature. Okay, how are they going to improve it? We have, this is the original signature. Have that right here. A more experienced Rustinian would write the signature shown in listing 4-9, this thing, because it allows us to use the same function on both string with a capital S values and the ampersand string, which is a string slice. So they would change it to this. And this is still work. Well, given that we take out this portion. And it does, it still works. If we have a string slice, we can pass that directly. If we have a string, capital S, we can pass a slice of the entire string. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. Okay, so what they're saying here is now, since we define it as this, we can take both this, which was the original, which is capital string, and if we wanted to, we can just change this to a string literal. Let's say hello world. Give it that. Let's not make it mutable. I don't think it has to be mutable. Can it be mutable? Let's check. Yeah, that works. And if we don't make it mutable, we haven't changed anything. That works too. So now our API can use both the capital string, the string that's defined on the heap, and the string that's put into the stack, or string slice that's put into the stack. All right. And they did what I did, which is some examples. They have string, they have the first word, they have a string literal, they have a pointer to a string literal, and They have the string literal. Yeah, now the API can take all of these different versions. That makes sense. Other slices. String slices, as you might imagine, are specific to strings, but there are more general slice types too. Consider this array. We have an array, A, 1, 2, 3, 4, 5. Okay. Just as we might want to refer to a part of the string, we might want to refer to a part of the array. And we'll do so like this. Same syntax. Same syntax. And the type is now, this slice has the type array of bytes that consist of I32. So integers, signed integers. It works the same way as string slices do, by storing a reference to the first element and a length. You'll use this kind of slice for all sorts of other collections. We'll discuss these collections in detail when we talk about vectors in chapter 8. And we have come to the end. This is the summary. So summary. The concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. The Rust language gives you control over your memory usage in the same way as other system programming languages. But having the owner of data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work. We'll talk about these concepts further throughout the rest of the book. Let's move on to chapter 5 and look at grouping pieces of data together in a struct. So that is the end of chapter 4, and in chapter 5 we're going to start on structs. Hope that was good. Hope that was entertaining. Hope that was useful. Aside of that, peace.